Okay, so in the last lecture, we had explained the 2 square theorem, and in this lecture, we will explain the 4 square theorem. The 4 square theorem. Okay, and the 4 square theorem, if I just write it as before starting even the discussion, that it's just an extension of the 2 square theorem. So it's just an extension of the 2 square theorem to 4 dimensions, and that's it. That's exactly what we require to do, to 4 dimensions. And the proof is exactly same as we did in case of the 2 square theorem, that is just an extensive use of Minkowski's theorem and nothing else. So what we actually require is just to show that there exists a non-zero lattice point inside a chosen ball, and using the criteria which we have predefined in case of the Minkowski's theorem. Okay. So let me first state the theorem. The theorem is as follows, that every positive integer is a sum of 4 integer squares. Is a sum of 4 integer squares. So you can verify this for any arbitrary integer. Our proof precisely lies in the fact that we will prove this for the primes. Okay, and we'll see why we are doing so. Okay, so we prove this only for primes p. Okay, now to prove this only for primes p, we just manually verify this theorem for the only even prime 2, which we can easily see that clearly. I can write 2 as 1 squared plus 1 squared plus 0 squared plus 0 squared, and we are good to go. Okay, so therefore, so assume p to be odd. So we can simply talk about only the odd primes. Now the first thing first, we claim that, and it is actually a very easy claim. We claim that the congruence u square plus v square plus 1 congruent to 0 modulo p has a solution u v coming from z. Okay, and why does this follow? So this just follow, this can be easily verified by just seeing the what happens if I say that it does not have a solution. Okay, observe that u square takes exactly p plus 1 by 2 distinct values, modulo p obviously, distinct values modulo p when u ranges. So I need u to be ranging over modulo p as well. So when u ranges over 0 1 till p minus 1, and when it does so, so it should also be satisfied by the other part of the congruent equation, which is minus 1 minus v square. Okay, therefore there exists a total of p plus 1 solutions. Okay, because I'll have p plus 1 over 2 distinct values of v of minus 1 minus v squared whenever v ranges in the provided range. The problem is that for the congruence to have no solution, then all these p plus 1 number of elements needs to be distinct, right? For the solution, for the congruence to have no solution, all these p plus 1 values in total, because I need to have a non-equality modulo p. So these p plus 1 over 2 values coming from the u part and these p plus 1 over 2 values coming from the minus 1 minus v squared part, all these elements need to be distinct so that the congruence does not take place. In other words, the total number of elements which we have, which is p plus 1 in total, all these elements needs to be distinct. So all these p plus 1 values needs to be distinct, but then you can just think of as fixing p and ranging over u, you will get only p of them, right? So this actually implies in total that p plus 1 is less than equals to p, which is a contradiction or which is absurd. Therefore it must have a solution. Clear? Okay. Yeah, so we are good to go now. So now, as I said, that we will just prove this for the primes, okay, and to prove this for the primes, what we typically do is that we extend our 2 squared theorem to 4 dimensions, and the rest of the things are exactly analogous to what we did in the 2 squared theorem. So let L in Z4 be a lattice consisting of the points A, B, C and D such that C is congruent to C is congruent to UA plus VB modulo P, and D is congruent to UB minus VA modulo P. Okay. Then, so now if I fix A and B, as we did in the 2 square theorem, there I had to fix only A. In this case, if I fix A and B, then I will get a P, so I have P choices for C and I have P choices for D respectively. So in total I have P squared distinct cosets of L in Z2 induced by L in Z2, or in other words, then the index of L in Z2 is Z4, or in other words, the volume of the fundamental domain of T, the volume of the fundamental domain is P square. Okay, and this exactly comes analogous to as we claimed in the 2 square theorem, and the rest just follows from the Minkowski's theorem, because now what I do is I just assume a bounded symmetric convex set which is large enough to contain at least one of the non-zero lattice points coming from the Minkowski's theorem. So, and for that the simplest case which I can do is that I can just assume a 4-dimensional sphere with center at origin, radius r. Now this will have volume pi square r square over 2, and we choose r in such a way that this happens. Okay. So choose a 4D sphere, center at origin, radius r, having volume. So if it has radius r, it will by definition carry the volume pi square r square over 2, and we choose r to make this value. This exactly abide by is the way we proved the Minkowski's theorem. We choose r to make this value greater than 2 to the power 4, because we are in 4 dimension, 2 to the power 4 times the volume of the fundamental domain, which is just 16 times P square. So let r be just or rather sorry r square be just 1.9 times P. Okay, and now typically we are done. Then by the Minkowski's theorem, there exists a non-zero lattice point. There exists a lattice point 0 not equals to A, B, C, D as the tuple of the lattice point belonging to L in this 4-dimensional sphere, and so their norm, or rather I can simply write as their distance from origin, which is a squared plus b squared plus c squared plus d squared. This must be less than equals to r squared, but r squared by assumption is 1.9 times p squared, sorry, 1.9 times p, and this is less than 2p, right? This is less than 2p. We are good to go. And this is obviously modulo p, or rather I can just simply speak of the fact. Further, modulo p, if I just put the respective values of c and d as we assumed to be the points in the lattice, we can observe that a squared plus b squared plus c squared plus d squared is nothing but congruent to 0 modulo p, right? But then we get the same sort of an argument as we did in the 2 square theorem, that is then under modulo p. So this basically means that a squared plus b squared plus c squared plus d squared is a multiple of p, is a multiple of p, precisely inside, so it's precisely inside the interval 0 less than it's precisely inside the interval, or I should write it like precisely such that 0 less than a square plus b square, because it's non-zero, right, d square, and it is seen to be less than 2p, or which immediately speaks of the fact that a square plus b squared plus c squared plus d squared is exactly equal to p, right? Okay, so now if I talk about any arbitrary natural number, so for now any n in Z, just prime factorize n, prime factorize n, and observe that. So whenever I prime factorize it out, I will observe that the product of two of the prime factors. So let me say it in this way, okay, or rather let me speak it about this in this way. Now suppose p1 and p2 are two primes such that p1 can be written as a squared plus b squared plus c squared plus d squared, and I can write p2 as capital A squared plus capital B squared plus capital C squared plus capital D squared from the 4 square theorem. Okay, this is a very simple claim to do because we have just proved the 4 square theorem for primes. But the only thing which you need to observe, which is just your elementary level mathematics, that p1 times p2, which can be written as a squared plus b squared plus c squared plus d squared, times capital A squared plus capital B squared plus capital C squared plus capital D squared, this you can just expand to be written as small a times capital A minus small b times capital B minus small c times capital C minus small d times capital D whole squared plus small a times capital B minus small b times capital A, plus small b times capital A plus small c times capital D minus small d times let me just check, c times capital D, so small d times I think I should get c correct squared plus AC minus B capital D plus C capital A plus D capital B squared plus I will get A capital D plus B times capital C minus CB plus DA squared, right? And so this still yields, so this product still yields a sum of 4 integer squares. So whenever you have n, therefore for all integers I can just consider the prime factorization in this way till pm let's say, and just consider them pairwise, just keep considering them pairwise. Then if you consider p1 and p2 pairwise, I know p1 has an expression of the form a squared plus b squared plus c squared plus d squared, and I also know that p2 has a expression of the form capital A squared plus capital B squared plus capital C squared plus capital D squared. If I multiply these two out, then I will get an expression of this form. Then simply consider this to be an integer, this to be an integer, this to be an integer, and this to be an integer. So you will have an expression in terms of 4 integer squares, and if I have p3 after that, then next just consider p this whole times p3, and you can just inductively continue this process to get whatever you require as the complete explanation of the 4 square theorem. Okay. So that's all for this lecture. In the next lecture we will talk about the geometric representation of algebraic numbers. Okay. So meet you guys in the next lecture.